Okay, this is going to be a very important problem to understand. You're going to get some problems like this on the Jedi trial, and it's going to be important to know what the thing is that is rolling down like some kind of a ramp. In this problem, we have a thin ring, but we might have a ball or you might have a disc. So what we're going to do in this problem is we're going to actually calculate the kind of an equation for any one of those things that you can use. So some of the other ELAB problems you have are going to be basically the same equation but with a different object that's rolling down an inclined plane. So you have an inclined plane, and in this particular case there's a thin ring up at the top rolling down, and it's 1 meter high. This is the h. I'm just going to put in h for now. Later it's 1 meter, and but we're going to derive an equation here. So put your seatbelts on. Okay, so this thin ring rolls down, and we're asking what is the velocity down here at the bottom. So here's where it starts, and then it gets down here at the bottom, and I want to know what the velocity is. So what we can do to derive the equation for velocity is to use the conservation of energy. So it has certain kind of energy up here, and then it has certain kind of energy down here, and the energy should be conserved. So whatever energy is at the top should equal all the energy at the bottom. Well, what is the energy at the top? Well, it's all potential, so it'd be mgh. So that's pretty easy. At the bottom, it's all kinetic, but there's two kinds of kinetic. There's linear kinetic, and there's also rotational kinetic. Linear kinetic is 1/2 mv squared, and rotational kinetic is 1/2 I butt squared. So this at the bottom needs to equal this at the top. So this is the same. You're going to do this for every derivation of something rolling down a ramp. So I start the derivation like this: mgh equals 1/2 mv squared plus 1/2 I butt squared. And we can kind of substitute some things in here. So I'll have mgh equals 1/2 mv squared plus 1/2. And so there, I'm going to sub a lot of these things in. What is the I value? This is a thin ring. So if you remember, for a thin ring, it was mr squared. So I'm going to put that in for the I, mr squared. And the other trick here is, what do I put in for the angular velocity? Because I don't know what it is here. Technically, I don't know anything in this problem. I eventually want to figure out velocity, so I should have a linear v in here somewhere. And if you remember, to find linear world, you take rotational world times the radius. So if I know the angular velocity, I can multiply it like in radians per second. I can multiply it by how long a radian is, and then I'd be in meters per second. So v equals butter. So what would the butt equal? It would equal v over r. And I could square that, so it'd be v squared over r squared. And this is a little trick. If you remember, we taught this right before we all went into quarantine, that you can put v squared over r squared in for the butt squared, and then your r squareds cancel out, see, and you don't actually even need the radius. That's the important part there. So I also have an m in every single one of these terms, so I don't need the mass either. That's why you don't have a mass in this problem, and you don't have a radius in this problem. So what am I left with then? I have gh equals 1/2 v squared plus 1/2 v squared. So gh would equal 1/2 plus 1/2 is 1, so I'd get v squared. And then I'd get v would equal the, I take square root of both sides, v would equal the square root of gh. So this is the equation for the velocity of a thin ring at the bottom of an inclined plane. And you'll notice the radius, the mass, all those things didn't matter. The only thing that mattered is gravity, which is going to be 9.81 each time, because we're going to be on the Earth, and the height. And so that's why the only thing that was given in this problem was actually the height, 1 meter. So it'd be this would be the square root of 9.81 since it was 1 meter. So that's how you find the velocity at the bottom. Okay, so what I want to do is, how would this change if we had, like, for say, a ball? So the I of a ball is 2/5 mr squared. And what if I had a disk? A disk is 1/2 mr squared. Okay, so if you just look at this, we'll be able to do this really quick. This is 1/2 mv squared, which is right there, and then 1/2 I butt squared. So this 1/2 stays there, and then in this part here, though, we'd have different things. We have an mr squared each time. See, we'd have an mr squared each time, but there might be a different fraction out here in front. So for a ball, what would it be? So I'd have GH equals 1/2 v squared. That part here would be still the same. Plus, so what would this one be? So if I had a ball, it'd be 1/2 times 2/5 mr squared. So this would be 1/2 times 2/5, and the 2's would cancel it. So I'll just write that in though. 1/2 times 2/5. So and then v squared. So you'd notice that the 2's would cancel out. So I can multiply this whole thing by 10, and I would get 10 GH equals 5v squared plus 2v squared. So I'd have 10 GH equals 7v squared. And the v would be the square root of 10/7 GH. So this is the equation for the velocity of a ball at the bottom of the ramp. So square root of GH was a thin ring. Square root of 10/7 GH would be a ball. What would a disk be? Okay, so for a disk, you'd have GH equals 1/2 v squared plus 1/2, and this time you'd have another 1/2 as your fraction of v squared. You should probably go through all three of these and write it out so it's a little bit more clear. So I'd have GH equals 1/2 v squared plus 1/4 v squared. So GH would equal 1/2 plus 1/4 is 3/4 v squared. So the v would equal 4/3 GH square root. So this is for a disk. So this was for a thin ring. This one was for a ball at the bottom of the ramp. And square root of 4/3 GH would be a disk at the bottom of the ramp. So you're going to get a problem, and I don't know which one of these things is going to be in, and I'll give you a different height maybe. But eventually, if you just know these equations, and of course you can use your notes on the tests from now on, so exciting. If you have these derived out here in your notes, you could just be able to use these and write that down. Okay, let's QED that. That was a big one. That was a big, important problem. I can't write the bottom of the E. There we go. QED. Okay.